All right. So in this video, we'll be looking at a different application in complex integrals. And this refers to what's called independence of path. So this reflects heavily on, um, I'll say with vector fields in Calc 3. And this reflects on the resulting integral for various contours in a vector field. Okay, in a vector field. So you should have seen this in multivariable calculus. So let's go over what it means. So independence of path. So essentially the value of the integral, complex integral rather, will be the same no matter what path you take from the starting point to the ending point. So if I have some domain D, and if I have some initial point A and some final point or a terminal point B, what an independence of path means is if I take, let's say, a straight path from A to B, that value, so if I call this path C here, C of, let's say, f of z dz, well, this is equivalent to, let's say, a path that looks like this, call this C1. So this may equal to the line integral of C1 f of z dz, or it could equal to the line integral of, let's say, a sinusoidal curve like this, right? This may equal to, let's call this path C2, right? So if you have an independence of path, the value of these line integrals will be the same, right? So the value would be the same. Okay. So let me write out the definition. So let A and B be points on a domain D, which is a subset of the complex numbers. Okay. A contour C is a contour C is independent of path if the value is the same for all contours C in D. With initial point A and final point B. All right. So that is what independent of path means. So for example, a integral may be independent of path in a gravitational field. In a gravitational field. Or in a magnetic field. Essentially, you've seen that the work done on a particle that's moving in some path would be the same, no matter which path that particle would take, right? In some gravitational field from A to B. So the work that's done going on this straight line path would be the same as the work done going on a curve or going on a circular path or even some line segment, right? So the possibilities are endless for a particle to travel, right? Never, what it boils down to is that the line integral of the contour, the line integral of the function by using those contours will be the same. Okay, so that's essentially what that means. Okay, and here is an important theorem. If we have an analytic function, okay, so suppose that a complex function f of z is analytic. Oh, that's not good. On a simply connected domain. D. And C is any contour in D. Then the line integral of f of z dz is independent of path. Okay, so that's pretty powerful, right? So if you have an analytic function on a simply connected domain, then you can say that the line integral of f of z dz is independent of path, right? It has to be analytic on every point in the domain D. So that's the key, all right? So here is an example of how the on what a line integral on a what a line integral would look like on just using this concept of independence of path here. So we want to evaluate this line integral dz. So we want to evaluate this line integral 4z minus 1 dz on this contour. So let's say here. Oops. Here's my real axis. All right, so what I'm saying here is so this curve C, so this whole curve C is comprised of two separate curves. So one of them is the arc of this circle of radius 1, I'll call it C1. And then C2 here is just the line segment going from, so this point right here would be 1, 0, so 1 plus 0 I, on up to this point, 0 plus I, right? Okay, so let me write out this in the in complex numbers. Okay, so here is, so this is just the brute force way of computing this line integral. Okay, so this curve C, well, it equals to the curve that is representing the quarter circle of radius 1 plus the line segment from 1 to I, right? 1 to I. So what we need to do is first we need to parameterize C1 and C2, right? So for C1, that is representing the arc of the circle, arc of the quarter circle of radius 1, right? So z of t, this equals to e to the it, right? Where t is in between minus pi over 2 to 0. Okay, you can use 3 pi over 2 to 2 pi. That would also work. All right. Yeah, so the circle, it has radius 1, and these would be the limits for t, right? Okay. C2, on the other hand, would comprise of the line segment going from 1 plus 0i to 0 plus I, right? To 0 plus I, this final point there, right? So z of t, so we need to write out the parameterization of a line segment. Okay, so that would be 1 minus t times the initial point. That would be 1 plus 0i plus t times 0 plus I, so t times I. And the limits for t would be from 0 to 1. Okay, so when t is 0, we'll have 1, right? So this would be 0, and this would be 1, right? So we'll have 1, and when t is 1, this will be 0, and this will be 1i, right? So we have the right parameterization, okay? So I'm going to rewrite this as 1 minus t times, so in this case, it's, I'm sorry, 1 plus t minus 1 plus I, right? Okay, I'm going to write it like this. Okay, so now let's look at the line integrals separately. So for C1, so the line integral for C1, so 4z minus 1 dz, this will equal to the integral from minus pi over 2 to 0 of 4 times, so in this case, it's e to the it. So, yeah, so in this case, it's e to the it minus 1. Let me rewrite this. It's a little bit cleaner. E to the it minus 1 times z prime of t. So in this case, it's I times e to the it dt. Okay. All right. And so this equals to the integral of minus pi over 2 to 0 of 4i times e to the 2it minus I times e to the it dt, right? And so this equals to, so I'll have 2 times e to the it minus e to the it, 0 to minus pi over 2 to 0, right? So okay, so this equals to 2 times e to the 0 minus e to the 0. E to the 0, right? It's the lower limit, and minus, oh, this is 2it right there. Okay, so I'll have 2 times e to the 2 times I times minus pi over 2 minus e to the I times minus pi over 2, right? E to the 0 is 1, so this upper quantity, this will be 2 minus 1, okay? Minus, so this first quantity here, so the 2's will cancel. So this is 2 times cosine of minus pi plus I times sine of minus pi, right? Okay. And this quantity here, so this is minus cosine of minus pi over 2 plus I times sine of minus pi over 2, right? Cosine of pi is -1, so so this term right here, this is -1. Sine of pi is 0, so that's gone. Cosine of pi over 2, this is 0. So this quantity here is 0, and this would be a -1 here. Okay, so we'll have a -2 plus I that's left over here. And then so okay. That will be -2 plus I, and this is all minus by 1. Okay. So in this case, we'll have a 3 plus I. That's the result for the circle. Okay, so hopefully that made sense. For the line segment, right, so z of t, this was equal to 1 plus t times -1 plus I minus, oh wait, yeah, that was the parameterization, right? And so the line integral of z2 of 4z plus 1 dz, this equals to the integral from 0 to 1 of 4 times, let me write this a little bit clearer. So 4 times 1 plus t times -1 plus I. Okay. So that's z -1. Yeah, that should be a minus. And then multiplied by z prime of t. So in this case, it's -1 plus I dt. Right? And so this equals to -1 plus I times the integral from 0 to 1. So I'll have a 4. So if I distribute the 4 along these two terms, so I'll have a 4 minus 1, so I'll have a 3 plus 4 times -1 plus I times t dt. Okay? So this equals to -1 plus I times the integral from 0 to 1 of 3 dt plus the integral from 0 to 1 of 4 times, let me actually write it this way, 4 times -1 plus I times the integral from 0 to 1 of t times dt. Okay. So this would equal to -1 plus I times 3t, going from 0 to 1. Plus, so this right here, this is t squared over 2, right? Just use the power rule for antiderivatives, right? And so this second quantity right here, this would be reduced down to 2 times minus 1 plus I times t squared. Okay. Went from 0 to 1. So this equals to minus 1 plus I times 3 plus 2 times minus 1 plus I. Okay, and so this equals 2 minus 1 plus I times, so it's 3 minus 2 is 1, so that we'll also have a 1 plus 2I, right? And we FOIL this out, so we'll have a minus 1 minus 2I, and then a plus I that comes from here, and then the outside terms will get a minus 2, right? So this would equal to minus 3 minus I. Okay? Therefore, the line integral of 4z minus 1 dz is equal to the line integral of c1 plus the line integral of c2, which we computed as, so we had 3 plus I here. Oh, I'm sorry. Oh, this should be a, okay. That should be a minus, so yeah, minus up front here too. Okay. Yeah, the minus refers to this symbol there. So yeah, this should be a minus I. There we go. My mistake. So we'll have a 3 minus I here. Okay. Plus this result here, right? Plus so we have a minus 3 minus I, right? The 3's cancel and we add the i's together, we'll have a minus 2I. And that's what we wanted. Okay? So it equals to minus 2I. Now, if you notice in our illustration here, we went through a ridiculous path, right? We don't really need to go through two separate paths. Instead, what we should have done is go along this path along the imaginary axis, right? So this is where the independence of path comes into play, right? If you notice, 4z minus 1 is a polynomial, so it's analytic everywhere on the complex plane. So all polynomials are entire, okay? So what that means is it's independent of path for just any starting point and any final point we choose in the complex plane. So, okay, if we choose the other path, which indicates this path here along the imaginary axis, okay, so if I call this C3, let's say, we should get the same result of minus 2I. So for C3, okay, Z of t, so we have to look at how we would parameterize this line segment, right? So it's 1 minus t times minus I plus t times I, okay? When t goes from 0 to 1. So in this case, we'll have minus I plus t times I plus t times I. So in this case, this will be I times minus 1 plus 2t. Okay, so 0, t is in between 0 and 1. Okay, T is in between 0 and 1. So that is the parameterization of that line on the imaginary axis. Okay, on the imaginary axis. So this line integral of 4z minus 1 dz along this curve C3, this would equal to the integral from 0 to 1 of 4 times I times minus 1 plus 2t minus 1 times z prime of t. Now z prime of t, so that would be, so that's 0, that's I plus another I, so that's 2i. Okay, so it's 2i. 2i, gosh darn it, 2 times I dt. Okay. And so let's actually integrate this. So this equals to 2i times the integral from 0 to 1 of 4 times, well, I'll just say 4 times I times minus 1 plus 2t minus 1 dt. Okay. So this equals to 2i times the integral from 0 to 1 of 4 times I of minus 1 plus 2t dt, minus the integral from 0 to 1 of dt. Okay, so this equals to 2i times 4i times minus t plus t squared. And this goes from 0 to 1. And then we'll have a minus t, and that goes from 0 to 1. Okay, so this equals to 2i times, well, okay, this would be, so the lower limit would be 0. The upper limit, this will be a minus 1, and we'll have a plus 1 here. So that's also 0. So therefore, this first term would be 0. Okay. And then this would equal to a minus 1 times a minus 1. And this equals to minus 2i, which is the same as the result that we had going through 2 separate paths. Okay. So this is the same as this result here. Okay. So hopefully that makes sense. So now we have this independence of path property. It'll be a lot easier to deal with complex integrals, okay? And we're going to use this similar concept as the fundamental theorem of calculus, okay, that you've seen before. So, let's look at a definition of an antiderivative. And this only happens if a function is continuous on a domain, right? So suppose f of z is continuous. On a domain D. If there shoot. So I mean capital F of z here, and this is lowercase f. So if there's this a capital F of z such that the derivative of capital F of z equals little f of z, then little f of, capital F of z, let me do this, then capital F of z is called the antiderivative. of little f of z. Okay. And then this will lead on to a important theorem in multivariable integration, right? And this refers to the fundamental theorem of contour intervals. And this will reflect off on the fundamental theorem for line intervals in multivariable calculus that you've seen. Okay. So suppose f is, so little f of z is continuous. A domain D, and capital F of Z is an antiderivative of little f of Z. Then point Z1. Z1 minus capital F of Z0. All right. So this right here is the fundamental theorem for contour intervals. Okay, it's similar to the fundamental theorem in line intervals in Calc 3, right? So if you have a continuous function, and if you know that capital F of Z is an antiderivative for little f of Z, then for any contour C that we define in D with an initial point Z0 and a final point Z1, the line integral of little f of Z dz is equal to capital F of Z1 minus capital F of Z0. Okay. And I'm going to go over a specific example, okay, on when we can use this fundamental theorem for contour intervals, and when we can't use it, right? And so okay. So here's an example. Here's a couple of examples. Okay, so we have these examples here. And I want you to try to work out these intervals on your own. Okay. So why don't you spend a couple of minutes on working on these intervals and see what you come up with. All right. So pause the video and try to work on this. Okay. So okay. All right. So I've assumed you worked on these examples. Let's actually work these out. So oh, 2z plus 1 squared. Okay, sorry about that. This should be squared. I'll give you a few more minutes to work on these examples here. So I meant a squared here. It's in the textbook. So let's work these out first. Okay. So on part A, we can do a U sub. Okay, we can do a U substitution. U is equal to 2z minus 1. And then du is equal to 2 times dz. All right. It works out just like that. So in terms of the u's, what we'll have here is, so with the lower limit, we'll have a minus 1 minus I. And the upper limit for the u's, so that's 2 times 1 minus I minus 1. So that's 2 minus 2I minus 1. That's a 1 minus 2I. And we'll have a 1/2 u squared du. And this would equal to 1/6 u cubed. 1 minus 2I and minus 1 minus I. This is 1/6 times 1 minus 2I cubed minus 1/6 times minus 1 minus I cubed. All right. So that's essentially what that equals to, right? I believe difference of cubes or sum of cubes. Yeah, so x plus y cubed. Three, it's y squared plus y cubed. Okay. That's how you do that. Yeah, so this is plug in 1 minus 2i and then minus 1 minus I into the x and the y's respectively. And you should be able to simplify that. You should be able to simplify that easily, okay? But I'm going to move on to the other example. So the other example is pretty important because this arc of the circle of radius 4, well, it refers to this piece of the circle, right? C is the arc of the circle. Okay. So what we want to do is yeah, so it's looking at the arc of the circle on the right circle here. So okay. So now 1 over z is analytic except at z equals 0, right? If it's at z equals 0, we can't really use the fundamental theorem for contour intervals, right? So we have to look at where, so f of z is continuous, right? So f of z being 1 over z, it's discontinuous at z equals 0, right? But we're only, so that's where the contour integral theorem is not applied, right? Everywhere else, it is applied, right? So if we're looking at the arc of the circle, we can apply this fundamental theorem, right? So, and then the antiderivative for 1 over z, what we have looked at in the past, the derivative of the principal logarithm of z is 1 over z. Okay, is 1 over z. So, right, so the derivative of the principal logarithm, so that would be its so the antiderivative of 1 over z is the principal logarithm of z. So so if I call this c, it would be and the natural log of z. Okay. All right. So this equals to yeah, so okay. I'm sorry, that's I and then minus I. So really, minus I here. Absolute value of the radius plus minus pi over 2, which is pi times I. Right? Which is pi times I. Okay. So that's a little bit on independence of path and the fundamental theorem for contour integrals. So to check for comprehension, here's some problems for you to work with. 2, 6, 10, 14, 15, 18, 20, 23, and 25. Okay. So we're moving right along with this course here. So in the next section, or next video rather, we'll look at Cauchy's integral formula. That's going to be really sweet and useful when we get into looking at different types of zeros in the complex plane and looking at Laurent series and how to formulate those. So stick around for stick around for Cauchy integral formula. So other than that, thank you for watching, and I'll see you all in the next video. So take care.